Hi, everyone. So I'm here today to talk to you, but I am really here representing the work of a whole lot of people. As you say, I'm Jessica Sandland. I am a principal lecturer in the Department of Materials Science and Engineering at MIT. But what I'm going to show to you today is really a collection of work of a lot of my colleagues, Joey Gu, a chemical engineer, John Liu, a mechanical engineer, and Alex Shvonsky and Michelle Tomasic, who are physicists. And we are all part of this group called the Digital Learning Laboratory. And actually, before I talk to you sort of about our courses and some of the things that we're doing in our courses, I'd like to talk to you a little bit about the Digital Learning Laboratory. But first, I'm actually curious who is in the audience. Do we have course developers, instructors in the audience today? Some course developers and platform developers, sort of. Sorry. Anyone I missed? What? UX designers. So we are a digital learning laboratory, and what we call ourselves is a community of practice that aims to advance digital education, both at our university and with our global community of online learners. And I think this word community of practice is really important to us. The idea that the word practice really to us implies that we are in the trenches, we are developing courses, we are interacting with students, we are getting feedback from those students, and we are able to sort of iterate and to develop courses based on the feedback that we get from our experiences actually developing courses and interacting with students. And we develop courses for learners at MIT, we develop courses globally, and we do so as a partnership. We are always acting as partners with faculty and also as a group to sort of advance the level and the understanding of what we can do with our online education programs. And we have basically two goals. We want to leverage learning science, and we want to leverage technology, and we want to leverage those two things to improve teaching and to improve learning. Here are some of my co-authors here. And what makes the Digital Learning Laboratory unique is that we're disciplinary experts. My colleagues in mechanical engineering, they hold advanced degrees in mechanical engineering. My advanced degrees in materials science and engineering. And we are embedded in departments. We are teaching staff, or perhaps sometimes teaching postdocs, who are embedded in individual departments across the institution. But we come together to learn from each other, to discuss, to innovate, to research together, to develop tools together. And we think those partnerships are really, really important to allow us to not sort of operate as separate islands in the Department of Biology or the Department of Mathematics, but as really a community who works together to have global impact, improve accessibility, and to innovate together in education. Where can you find our courses? You can find the work that we're doing at learn.mit.edu. Not everything at learn.mit.edu is work of the Digital Learning Laboratory. There's a whole bunch of content here. You can find open courseware course materials, you can find professional development materials. But if you take a look at our MOOCs, so free courses where maybe you can get a certificate, a lot of that content has been developed by the Digital Learning Laboratory, and you can find hundreds of different courses, mostly courses that fall into this category of sort of advanced science, advanced engineering courses. Some of the examples of what we've done reasonably recently, computational data science and physics, analysis of transport phenomena in fluid mechanics. This one is one I've worked on, electrical, optical, and magnetic properties of materials. And I think one of the questions that sometimes we like to pose is, if we want to reach millions and millions and hundreds of millions of learners, we are not necessarily going to do that with advanced graduate chemical engineering classes, right? So I think it's fair to ask, what are the motivations and what are the benefits that we see of dedicating time and effort? Why do departments want to devote time and effort? Why do professors want to devote time and effort to developing these advanced online courses? And I sort of break this down into 3 different categories for myself. And the first one is really, it reflects who we are. The courses that we're making, these MOOCs that we're making that are based on advanced engineering and science courses, this is really a reflection of the MIT experience. This is a reflection of the experiences that our undergraduates and our graduate students have when they are at our university. They also represent sort of our priorities in what to teach. So for example, I come from a small department. There are not many of them, not many material science and engineering departments in the United States, maybe 60 of them across the country. And we'd sort of like to really put our stamp on what it means to teach material science and engineering. We want to be able to assert, this is what we think should be included in a curriculum, and this is how we think it should be taught. And these classes give us one opportunity to really do that. And allows us to sort of set the standard for teaching, set the standard for curriculum in our fields. We also think that it's really important to expand access to this expert knowledge. We are teaching classes that include materials that's really difficult or maybe even impossible to find elsewhere. And we're teaching classes that are often taught by faculty who really define their field. So this is sort of my favorite, example. You're taking courses by professors who really wrote the book on the subject. And in this case, I had collaborated with Professor Lorna Gibson. She wrote the book, Cellular Solids, with her collaborator, Michael Ashby. And she gives a MOOC on learn.mit.edu called Cellular Solids. And I think we think it's a real service to be able to share that kind of expert knowledge with this global community of learners. Another thing that we're very excited about, and this isn't true in all of our departments, but in a lot of our departments, there are really viable pathways that exist that can take a student from a beginner sort of, and I use the word beginner, maybe a talented high school student who has taken some high school chemistry, taken maybe calculus at the high school level. And you can really work your way through the curriculum and get to a graduate level course step by step by step in our curriculum. And another thing that we find is that these sorts of courses have really given us an opportunity to explore some multidisciplinary and interdisciplinary fields that we might not necessarily do so much in our classrooms. So one example from my friends in the physics department is this class on computational data science in physics, which both has sort of heavy physics components, but also a very rich data science component. And I think that this third point is probably one of the most essential ones for us. Developing these courses really gives us a chance to create scalable, reusable educational resources that we get to share, that sort of motivate us sometimes to create. In a lot of these classes, maybe we have 10, 15, 20, 25 students in our classroom, and we take the time to develop these fairly complicated learning resources for their benefit. It feels like a much more worthy endeavor when we get to share these with learners around the world who are interested in the work that we're doing, with teachers who may be interested in employing some of these classes. We also find that these materials can be really useful in preparing our researchers. If we have undergraduates or graduate students who are coming into the laboratory for the first time, they need to learn a particular subject. They need to take a little bit of a deep dive. This is an opportunity for them to do that. Sometimes we also find that we are able to develop classes in this online format that really allow us to go deeper than we're able to go in our residential courses. I mean, those of you who teach at universities know that time is always limited, right? In this case, we can create our digital textbooks and we can put whatever we would like into those textbooks, and those are available for the students, those are available for their study and for them to take deep dives as they're interested. And these courses really provide us a direct connection to our residential courses. And we have so many use cases of sort of co-use of our MOOCs in our residential courses. And this is a case example that was shared to me by my physics colleagues, Michelle Tomasic and Alex Shavonsky. Our physics department teaches 2 courses that all of the students at our institution are required to take. So if you are going to be a mechanical engineer, you need to take 2 physics courses. If you are going to major in French, the French language, you need to take 2 physics courses. If you're going to be a political scientist, you also need to take 2 physics courses. So they teach the whole university. And they do it in a way that is highly influenced by the work that they've done on the MITx platform. So before class, it used to be that we gave students, readings from physics textbooks, which they didn't do, and then we complained that they didn't do them. And, we have all been there, right? So instead of the readings that students don't do, they get videos to prepare for class. Now, of course, there's always the risk that they don't watch the videos. So in addition to videos to prepare for class, they get concept check questions that check their knowledge of the video that they were asked to watch. And in fact, because the physics department, I think, rightfully concludes that it's not completely fair to grade students on material that they didn't have a chance to talk to faculty about, talk to their TAs about. They even have a system where if you got a problem wrong and you can explain why you've got a problem wrong, well, you can still get full credit for the class anyway, or full credit for the problem anyway. So they've sort of developed this method for preparing their students for what's going to happen in the classroom, which includes a short review lecture. But the priority that the physics department has for their class time is now group work, right? Now we're offline entirely. We're sitting around at tables. There are TAs walking around the class. And instead of students spending the majority of their time listening to someone like me standing up in front of the room and talking, they're working together actively. And they're sort of using the resources that we've developed for these MITx courses to enable this active learning, activities in their classroom. And after class, they're still relying on this MITx platform. So the students are all required to complete problem sets on a weekly basis. They do not actually do them online. What the physics department uses is they use these problem set checkers where students can enter in their answers, and it will tell you if you've got the problem right. They'll tell you if you've gotten the problem wrong. You still have to write up your problem. You still have to submit a written problem to your TA who will grade it, who will give you feedback. But now when you think you've solved the problem, yes, I'm correct, and that's great to know. Or no, I've made a mistake. And instead of waiting for 2 weeks to get the information that, yes, I've done something wrong, my TA has graded this, they've handed it back to me, we've moved on to another topic and I've forgotten about it. Now immediately the student knows that there's a problem. They're able to revise. That's great for them from a credit standpoint, but it's great for them from a learning standpoint as well, because they are able to sort of iterate on their work until they get it right. I've been at universities for many years. I have never seen anything so popular amongst the student body as these answer checkers. If you ask, any student who's used them, they almost universally say like that this sort of thing is really very helpful to the work that they do. So what did the students gain? Students come uniformly or more uniformly prepared for class. I think it's particularly hard in freshman classes, first-year classes, and first-year classes that require a lot of mathematical background to make sure that everyone in the class is on the same page. This definitely helps. As I said, they're no longer reading the textbooks. There's more time for active learning. It's also a nice way of getting students multiple exposures to the same idea. I think we've all been in classes where a professor is lecturing and you just don't kind of learn in the way that they explain things. And in this case, the physics students have an opportunity to hear from the professor online, but they also have an opportunity to hear from the professor in the classroom. And they also have an opportunity to hear from the TAs who are walking around the classroom helping them with their problem solving. So the students now have sort of these multiple exposures to the same material, which hopefully helps to sort of reinforce their learning. These were also developed in a very modular fashion to make sure that, every year classes change a little bit, things evolve a little bit, but because the content is modular and because it's been developed by multiple faculty members, every year, whoever's running the course can choose the relevant material, and this course and these course materials can be reused year after year. And finally, they really prove to be important resources for the students as they prepare for their examinations. They can go back, rewatch lectures, rework problems, and do that sort of thing. I have a question for you. We at our institution, our online program and our residential program, they're very, very, very closely connected. And I'm curious in the audience, do you have course content that's shared between your in-person and your online, in-person and online formats? Or do those two things tend to be very separate where you are? Would anyone like to sort of speak to what they do at their university? Do I have any volunteers?
Hi.
Hi.
Martijn Klabbers from Eindhoven University of Technology.
Nice to meet you.
Likewise. Yeah, we have, well, as a department, so I'm at the mathematics and computer science department. Mm-hmm. We have a lot of service education, mm-hmm. And yeah, through the Canvas, the learning management system, mm-hmm. we share a lot of this material. Mm-hmm. That's both online and in on-campus format. Mm-hmm. Most of it is of course kind of combined, blended. So in that sense, it's there's no real difference between the two. Mm-hmm. And it's also mandatory because, well, we try to have this service education as efficient as possible, and therefore every other department has to follow it in the way that we provide it. Sometimes also to the kind of detriment or the regrets of other departments that
you are the model that they need to.
Well, the model, I wouldn't say so, but that's a bit of the. We also have some courses on Coursera, for example, that mm-hmm. are offered as a flipped classroom mm-hmm. On campus, and there you see some but most of it, so most of the online material that we have on Coursera is not used or barely used on campus, and all the material on campus is not used in an online fashion.
Tend to be more separate.
Yeah.
What you share on campus with, you said Canvas, right?
Yeah.
Is that material that's usually sort of is the uptake usually by other faculty members at other universities, or is that sort of direct to other students?
We're developing that material ourselves. So yeah.
I'm curious who's using the material when you share it externally.
There you have to have a good connection between the professors of different universities, whether they want to use that indeed in their environment as well. But if you don't have the connection, it's never going to be used. So that's a bit of the link that
Very nice. Does anyone else have a story? I could maybe pass it down.
I am Christian from École Polytechnique Fédérale de Lausanne. So we have courses that are in flipped class as well. For example, the numerical analysis. So the course is either given, it's given in flipped class. So students have to take the videos at home and the quizzes, like the checking knowledge, and they get points for that. A very small amount, but that counts for their grade at the end of the exam. But we have another example where the prof uses his videos, his MOOC as a like you can watch the video before you come to class, and then he gives the same class as the video, but maybe in more details. So you can either take them before to understand better the class, or you can take them after to refresh the material.
And I'm curious, the students who do sort of the MOOC content in the flipped classroom way, are they actually do you have a separate instance for your students at the university, or do they actually participate in the MOOC with the students from around the world?
No, they don't participate with the around the world
it's
people.
It's different.
We have two instances, one for the public, and this is separate, and one for our students.
Great. Thank you, guys. Does anyone else? Okay, I'm going to go on. I'm actually going to skip through. So, what sort of strategies do we use? I think we are teaching we're teaching hard materials. And I just want to give you some stories, basically, of some of the different tools that we like to use to make this happen. I think many of you are familiar with the open response tools that are available. I think that this is one that we make a lot of use of in some of our sort of more in-depth courses. In particular, we have a program called MicroMasters program, which the students can use if they take a short selection of courses. Their performance can be used as sort of part of their admissions criteria. If they do well in the course, they could be admitted to a master's program at our university or at partner universities, and they can actually receive credit for the courses that they take online if they're admitted to programs. And so, especially in these sorts of programs, we want to make sure that students are doing work that's equivalent to what they would really be doing on campus. There are basically two different tools we use to do open response, the native one on Open edX. We're actually also, many of us in the Digital Learning Laboratory use an LTI tool through Feedback Fruits that we're very happy with, that allows us to do some more kind of open discussion that surrounds the peer review process. So it's not just kind of black box switching assignments to grade, but a bit more of a community that's discussing assignments together. And these open response assignments can range from very basic to, I want to take you through kind of a pretty complicated one. that was developed by my colleague John Liu for his MicroMasters course, Fundamentals of Manufacturing Processes. Now, I am not a mechanical engineer, so you'll have to bear with me here. But my understanding is one of the kinds of activities that mechanical engineers get very excited about in their classrooms are what they call disassemble, analyze, and assemble activities. So the idea is that if you can, if I can take a computer apart, or if I can take an iPad apart, and I can look at it and I can understand how those pieces come together, I can start to understand this technology as a system. I can start to understand the manufacturing process that went into developing, this piece of technology. And I can kind of understand the whys, as why certain manufacturing processes were used in developing, this piece of technology. But you can't do that online. I can't hand out a Kindle to every student in an online course and have them take it apart. And so John identified that augmented reality might be a really good way of sort of recreating this experience in a way that was scalable to lots of students. And so they actually developed both a Android app and a iPhone app that allows you to, disassemble a Kindle and examine it. I'll show you an example soon. But then they put this all together into a learner project where they use the peer review tool to ask the students questions, to ask them to think deeply about this experience. And so let me just show you some screenshots from a little movie from the app that they developed. So here is your iPad. It's not an iPad, it's a Kindle. You can take its components apart. You can see all of the different bits and pieces. You can examine it. And in a moment, they're going to let you look at this even a little bit more closely. So we have taken it apart. Now we want to inspect it so we can zoom in. And for the mechanical engineers, I understand that we get lots of information from these details that you're seeing in this augmented reality app. And so the students are sort of guided through this process, all right? Sorry. Guided through this learning process via just a whole set of challenge questions that ask them to think really deeply about the interactions that they've had with this AR Kindle disassembling experience. And then this goes into the peer review system. The students evaluate each other's work. The students discuss each other's work. They contribute to one another's thinking, and hopefully, come out of this having had an experience that's far more like what they might be able to have in a laboratory or in a classroom where they could actually sort of deal with these components hands-on. Another sort of critical, a critical component in a lot of our courses is this MIT grading library. And the MIT grading library was developed by one of my former colleagues, Julian Bloomfield. I'm so glad he did this because he's enabled so many things for us. This is a Python library of configurable Python classes. And you can find all sorts of information about this library at this link. There is a sample course available at this link that provides, there are so many examples of what this grading library can do. I highly encourage you to take a look. And there are just lots and lots and lots of creative ways of grading strings and formulas, matrices, lists, all sorts of mathematical expressions. You could probably spend a couple hours just getting lost in the examples that Julian gives here. For me, it's enabled a lot of, it's allowed us to do a lot of things that we couldn't do with the standard formula graders. One of the big ones was factorial expressions. We can now enter factorial expressions. This comes from a class that I've worked on called Microstructural Evolution of Materials, and it gives like an introduction to statistical mechanics. And if we can't make these expressions, we really can't talk sensibly about statistical mechanics in any way. We can solve eigensystem problems. We can enter imaginary numbers. This is a real robust grader. You can enter these in any order in many different ways. If it is correct, it will be graded correctly. You don't have to worry about telling students to enter things in particular formats, in particular orders, and also being able to work with imaginary numbers, also very sort of essential for us. We are also able to use really detailed variable names. And this, for me, became really critical when we decided to teach a course called Thermodynamics of Materials. And thermodynamics has these very complicated, very complicated variable names. You do not need to know what any of this means. But this is just one variable name. And this is telling you that we're talking about the heat capacity at constant pressure. Doesn't have to be constant pressure, could be constant volume. I'm telling you that we're talking about the heat capacity in a liquid phase. We might have a solid phase. We might have material scientists talk about many different kinds of solid phases, so that could change in many ways. Here we're talking about iron. Whenever we're talking about these sorts of thermodynamic variables, we're always talking about solutions, so maybe that's copper, or maybe that's chromium. And so for us to make meaning, we need all of these little details, or we can't turn this variable into something that like really means something to us. So this has been very powerful. But I have another question. Well, I'll tell you what my first question is kind of, we can do this. We do this. Should we do this? Is this too complicated? And my question for you is like, how do you guys decide how to balance rigor and approachability? Because this kind of thing definitely maintains rigor, but it is not super approachable for students. We give them things to copy and paste. They don't have to come up with these from the top of their heads. But like, I'm curious what the room's philosophy is when it comes to balancing these two factors. Is it always important for you to maintain rigor? Do you want to make courses more approachable for your students? Does anyone want to share their thoughts? John.
I come at this from the perspective of an instructional designer that appreciates edX's robustness, open edX's robustness. So I am always trying to push rigor and authenticity. Mm-hmm. And when I have to curtail that for approachability, for me at least, it's often because of the faculty. Mm-hmm. The faculty, there is a choice to make of whether the faculty can maintain that level of rigor that they want, which looks a little bit different than what you're kind of showing here. Mm-hmm. But it often, the bottleneck is often the faculty. So it comes down to what they want to maintain and what they're able to do to keep up that rigor. That's my perspective.
I'm curious, John, like, do you have any like good examples of like particular bottlenecks your faculty run into where like they think they just can't?
Sure. I mean, imagine that you have a assessment with. We'll take the peer review for a second. Mm-hmm. Like, we've deployed the open response assessment in our edX courses, and we give our students strict deadlines. We find that some of those students miss those deadlines. And they will then go to the faculty, and it's the faculty's job to make sure that they kind of hand grade, and then the faculty get tired of that. And the faculty say, I don't want to do this anymore. So let's switch to something that's like a reflection or something easier. So that's the kind of bottlenecks that we hit sometimes there, where we have to scale back the rigor to make it more approachable.
I know sometimes one of the questions I often sort of run into with the peer response system is like, I'm sort of very comfortable asking someone to write a 2-3 page essay and have it peer reviewed and not have, you know, the students receive faculty feedback and whatever. But is it fair to make someone write a 10-15 page paper like that? There seems to come a point where that feels a little bit excessive without that sort of more formal feedback. Anyone else want to share their thoughts? Should I keep going? Yes, please.
Yeah, thanks. What we interesting. I think we have a similar faculty approach. So there's a lot of stress on rigor. A lot of faculty that does actually live for that at the university. Mm-hmm. And not so much for approachability. Mm-hmm. And for example, in developing MOOCs, that was one of the things that we were hit hard in the numbers of drop-offs. Mm-hmm. Because then you see that people have too much of an idea of, well, this is the course that everybody wants to follow, but at the first kind of assessment, they drop off. Yeah. So this is one of the things that we indeed struggle with. One of the experiences that we have in creating, for example, a course on programming, is that we use the Jupyter Notebook solution, and there we introduce the topic very softly. Mm-hmm. So it begins with really simple exercises, and that helps. And this teacher is so fond of it, he does even do his lectures in Jupyter Notebook. So that's a bit of the technical approach that is increasing the approachability of these courses.
Yeah. And I think it's always, we teach these things to our students residentially, and they're hard there, right? But there's a TA there, and there's a faculty member there, and it gets that much more difficult, trying to figure this out when you're an independent learner. And this sort of leads into some of the things that I'm sort of thinking about here is, ways we design to support learners and things we think about in supporting learners. And we definitely add, scaffolded content and tutorial content that we really don't tend to use so much, with our residential students. I'm not sure if that's necessarily a good choice or not, but we sort of tend to expect that, the basic level, they will catch on to, first time through in lecture. But with our online students, a lot of times we want to sort of give them an opportunity here to, just look at some of the basics, do a multiple choice question, just kind of get their feet wet and make sure that they understand the fundamentals really well before we move them on to bigger, more complicated things. This is actually a residential example, again, from my physics colleagues. Where they took their MITx online course and used it really very much as kind of a repository, not a repository, but a source of problems for their residential students in basically two different ways. They thought of they think of their MITx online course as an online textbook. And so they can use it, one, to provide more practice problems to students. And, I think we all know students always want more practice problems. That's the first thing that they're, at least our students are always asking for. But they also used it to do a little bit more active learning in class. They draw from the problem banks in the MITx online course to use to develop clicker questions so that the professor can ask, a multiple choice question that they can, thank you, that the students can answer A, B, C, D, it's not a full active learning, course experience, but, just to get the students a little bit more engaged in that lecture. We're also very, very careful about our work solutions, and we're also very careful to provide very detailed work solutions. So this is just, an example from like one part of one problem in one course, and it goes on for quite some time. We just want to make sure that, again, because the students don't have a TA to ask, because the students don't have faculty to ask, we have discussion forums where they can sort of approach some of these things. But we really want to make sure that, everything has been spelled out for them if they've gotten the problem wrong, or potentially if they've solved it correctly, but I actually want to see how the faculty approached it themselves. So that is all I have for you today. I really appreciate your 40-some minutes of attention this afternoon. And I'm happy to take any questions you might have.
Hi, so you talked about some of the customizations. That custom Python library was really interesting. There's that LTI that was built by Quality Fruitland or something. I don't remember the exact name.
Feedback fruits, I think. I like Quality Fruit.
I'm just wondering if there was anything else that doesn't come out of the box in OpenEdX.
I mean, I think there are actually a lot of things that are going on that don't come out of the box that aren't captured here. Off the top of my head, one of the things that my math colleagues had developed was sort of a sketch tool where students can kind of draw freehand, an approximation of a curve, and it can look for inflection points, and it can look for maxima and minima, and make sure that students have kind of this this basic understanding of like what the shape of the function that they're talking about should be. So that's one bit of development that just comes to the top of my head. I am quite sure that there are others. But
Was something like that? I think you sort of suggested that was developed in-house at MIT.
in-house, yes,
Okay.
yes.
I'll build right onto your question, Stephen, and just say, what is the next thing that you want to have in OpenEdX, but maybe haven't been able to build or are actively building?
I think right now, like everyone else, all of the talk is about AI. I think all of the talk is about AI tutors and AI graders and how we can leverage, this crazy new world that we're living in to try to really better educate our students. And I feel like I am seeing things that are making me really very enthusiastic about that. The idea that you can have this tutor helping you along in your educational experience. There are so many ways that could go wrong, but there are a few ways that can go really, really, really right. And so I think that's just where everyone's attention is focused these days.
I think we might have time for one more quick question.
Hi. I would like to ask you if you have any numbers of the students, if they come to class more than before, after these new, or less, and if you have some numbers about the results of the students, if they are better than before or...
So, okay, this is the one difficulty of sort of representing my physics colleagues here. I don't know anything about the question of numbers and who is coming in is not in their classes. I do believe, like, qualitatively, they feel that their students are sort of more evenly prepared from this kind of preparation, and are sort of more likely to pass the class at the end. But I don't have. That's just kind of more in general. It's not like, oh, it's twice as many. I don't have those numbers. I could find them out for you if you want to talk afterwards.
Thank you very much.
All right, I think that is it. Thank you so much for the talk.
Thank you all. I really appreciate it.